In 1974, a young physicist named Stephen Hawking was working on a problem. He was thinking about black holes. The common wisdom at the time, based on Einstein's relativity, was simple. Nothing escapes a black hole, not even light. They were the universe's ultimate prisms. But Hawking brought a new tool to the problem. He mixed Einstein's theory of gravity with the strange rules of quantum mechanics. He wasn't trying to prove anything grand. He was just doing the math. The math showed something impossible. It showed that black holes weren't completely black. They leaked very, very slowly. They radiate energy. This became known as Hawking radiation. The idea comes from quantum physics. Empty space isn't really empty. It's filled with pairs of virtual particles that pop into existence and then annihilate each other almost instantly. But if this happens right at the edge of a black hole at the event horizon, something can go wrong. One particle might fall into the black hole while the other escapes. The escaping particle looks like radiation. To pay for the existence of this escaping particle, the black hole has to give up a tiny bit of its own mass and energy. So, over incredible spans of time, black holes evaporate. A black hole the mass of our sun would take 10 to the power of 67 years to disappear. That's a 1 followed by 67 zeros. It's a number so large that the current age of the universe, about 13.8 billion years, is an insignificant rounding error next to it. Hawking's calculation was pure theory. We have never directly observed Hawking radiation. The signal is far too weak for our current instruments, but his work changed everything. It showed that black holes have a temperature. It linked gravity, quantum mechanics, and thermodynamics. It was a clue, a hint that our separate theories of the universe were all part of something bigger. And it was all done with a mind, a blackboard, and mathematics. It makes you wonder, if one person's insight can change our view of the cosmos, what could we learn if we had better tools? What happens when we can build machines that can test these ideas directly? Number 19, we might need to break physics to explore the universe. The USS Enterprise from Star Trek moves faster than light. The ship itself doesn't. Instead, the space in front of it contracts and the space behind it expands. The ship rides this wave of space-time. It's like a surfer on a wave. The surfer isn't moving through the water faster than the wave. He's just on it. This idea, called the Alcubierre drive, was proposed in 1994 by a Mexican physicist named Miguel Alcubierre. He did the math. It's consistent with Einstein's theory of general relativity. The math works. But there is a catch, a huge one. To make the space in front of the ship contract, you need something called negative energy density. And we don't know if negative energy is real. Quantum mechanics suggests it might exist in tiny amounts for very short periods, something called the Casimir effect. But we've never seen a chunk of it. We don't know how to make it. To power a small warp ship, Alcubierre's original paper suggested you would need the energy equivalent of the entire mass of the planet Jupiter. Later refinements brought that number down, but the energy requirements are still astronomical. And there's another problem. A person inside this warp bubble would be causally disconnected from the outside. You couldn't steer it. You couldn't stop it. You would turn it on, and it would go. A 2012 study showed that any particles swept up by the front of the bubble would be released at the destination with incredibly high energy. You might arrive at your destination and vaporize the entire star system with a blast of radiation. So while the idea is fascinating, it's not just an engineering problem, it's a fundamental physics problem. We would need to discover and learn to manipulate a form of matter and energy that might not even exist. But if we could, the implications are profound. A trip to Alpha Centauri, our nearest star system 4.3 light years away, would still take over 4 years traveling at the speed of light. With a warp drive, the trip could theoretically take a few weeks or days, without the traveler experiencing any time dilation. It would open up the galaxy, we could go and see what's out there, we could test our theories about exoplanets by visiting them. It remains the ultimate dream of interstellar travel, a piece of technology that would require us to rewrite our understanding of energy and matter. Number 18, the universe might have shortcuts, but we have to build the doors. A wormhole is a theoretical tunnel through space-time. It could connect two very distant points in the universe. It's like folding a piece of paper in half and poking a pencil through it. The pencil is the wormhole. The distance through the wormhole is much shorter than the distance across the paper. The idea comes directly from Einstein's general relativity. These Einstein-Rosen bridges are valid mathematical solutions to his equations. They appear in the math of black holes. The problem is that naturally occurring wormholes, if they exist, are thought to be microscopic, on the scale of 10 to the power of 35 meters. They are also believed to be incredibly unstable. They would pop into existence and then snap shut so fast that not even light could get through. To create a stable, traversable wormhole, you would again need that same magic ingredient from the warp drive exotic matter with negative energy density. You would need to prop open the throat of the wormhole to keep it from collapsing. The amount needed would be immense, but let's say we could make one. What could we do with it? A wormhole isn't a method of travel in the traditional sense. It's a destination. You'd have to get one end of the wormhole to where you want to go. One idea is to create a microscopic wormhole in a lab, then use a powerful particle accelerator to expand one end. Then you'd put that end on a spaceship and fly it at near light speed to a destination, say the Andromeda Galaxy, which is 2.5 million light years away. The trip would take over 2.5 million years from Earth's perspective. But due to time dilation for the crew on the ship, it might only take a few decades. When they arrive, they place their end of the wormhole in orbit. Now, you have a permanent bridge, or a doorway. You could step from our solar system into a solar system in Andromeda. This would be, the ultimate astronomical tool. We could send probes through to study a different galaxy up close. We could analyze the composition of its stars, the nature of its dark matter distribution, and the planets around its suns. We could answer a fundamental question: is our galaxy typical, or are we an outlier? Are the laws of physics exactly the same over there? A wormhole would turn cosmology from a science of distant observation into a science of direct exploration. The challenges are enormous, perhaps insurmountable, but it's a possibility that exists within our current understanding of physics, waiting for a breakthrough in our understanding of matter. Number 17, to explore the stars, we might need to send machines that can build themselves. The distances between stars are the biggest problem in astronomy. The Voyager 1 probe, launched in 1977, is the farthest human-made object from Earth. It's traveling at about 38,000 miles per hour. Even at that speed, it would take it about 75,000 years to reach Alpha Centauri if it were heading in that direction. Sending humans is even harder. A multi-generational ship where the descendants of the original crew are the ones who arrive is a popular idea in science fiction. But it's a logistical and ethical nightmare. There is another idea proposed by the mathematician John von Neumann in the 1940s. He was thinking about machines that could reproduce. He called them universal constructors. Applied to space exploration, this is the concept of a von Neumann probe. You build one complex, intelligent probe. Its primary mission is to travel to a nearby star system. Once it arrives, it uses the raw materials it finds there, asteroids, dust, planetary matter, to build copies of itself. It would use advanced 3D printing or molecular assembly and robotics. It would mine for iron, silicon, and other elements. It would then launch these new probes to other star systems. This creates an exponential expansion. One probe becomes two. 2 become 4, 4 become 8. Even with slow conventional propulsion, this cascade of self-replication could explore the entire Milky Way galaxy in a relatively short amount of cosmic time. A 1981 study by Frank Tipler calculated that with speeds of just 10%, the speed of light, such probes could colonize the entire galaxy in less than 10 million years. That's a long time for a human, but it's a blink of an eye in the 13.8 billion year history of the universe. These probes wouldn't just be copy machines, they would be our eyes and ears. Each one would be a sophisticated scientific station. It would survey its star system, analyze planets, search for life, and send all that data back to us. The entire galaxy would become a network of sensors. We could get a complete map of every star, every planet, every nebula. We could solve the Fermi paradox. The paradox asks, if the galaxy is full of potential life, where is everybody? The existence of von Neumann probes makes this question even sharper. If an alien civilization had ever built them, their probe should be here by now. The fact that we don't see them is a profound mystery. Maybe no one has built them. Maybe they are deliberately hiding, or maybe we are the first. Building our own would be one way to find out. The key technologies needed are advanced AI, robotics, and some form of additive manufacturing that can work with unrefined materials in zero gravity. We are not there yet, but the individual components are all things we are actively developing. Number 16, the sun's power, bottled for a journey to another star. Our rockets today work by chemical combustion. It's basically a controlled explosion. This is very powerful for getting off Earth, but it's very inefficient for long-distance space travel. And you need to carry all your fuel with you. The more fuel you carry, the heavier you are, and the more fuel you need to move that fuel. It's a vicious cycle called the tyranny of the rocket equation. Nuclear fusion offers a way out. Fusion is the process that powers the sun. It involves smashing light atomic nuclei together, like hydrogen, to form a heavier nucleus, like helium. This process releases a huge amount of energy. A fusion reaction releases nearly 1,000,000 times more energy than a chemical reaction with the same mass of fuel. A fusion rocket would take a small amount of fuel, like deuterium and helium-3, and use powerful magnetic fields or lasers to heat and compress it until it fuses. The resulting superheated plasma would be directed out of a nozzle to create thrust. The advantage is efficiency. A fusion rocket would have a much higher specific impulse, which is a measure of how much push you get from a certain amount of fuel. This means you could travel much faster and for much longer. A trip to Mars, which currently takes 6 to 9 months with chemical rockets, could be done in 30 to 90 days with a fusion rocket. A trip to the outer solar system, to Jupiter or Saturn, would be cut from years to months. But the real prize is interstellar travel. A fusion-powered spacecraft could potentially reach 5% to 10% the speed of light. At 10% the speed of light, a trip to Alpha Centauri would take about 43 years. This is still a long time, but it's within a human lifespan. It makes a crewed mission to another star system a real possibility. We could send probes that would get there in decades, not millennia. The challenge is building a fusion reactor that is small, lightweight, and powerful enough for a spacecraft. On Earth, experimental fusion reactors like ITER in France are the size of large buildings and require massive amounts of power just to run. Miniaturizing this technology is a huge engineering hurdle. We need to create and contain a star in a magnetic bottle. But research is progressing. Several private companies are now pursuing compact fusion reactor designs. If they succeed, it wouldn't just revolutionize energy on Earth, it would give us the engine we need to finally leave our solar system and become an interstellar species. This would allow us to directly study other stars and their planets to see if their chemistry and geology are similar to our own. Number 15, building a copy of the universe inside a computer. The universe is complicated. The interactions between gravity, matter, dark matter, and dark energy over 13.8 billion years have created the vast web-like structure of galaxies we see today. We try to understand this with simulations. We take our best theories of physics, put them into a supercomputer, and see if we can grow a universe that looks like the real one. These simulations, like the Millennium simulation in 2005 or the more recent Illustris TNG project, are incredibly powerful. They use billions of virtual particles to model the formation of galaxies, but even the best supercomputers are limited. They are based on classical bits, which are either a 0 or a 1. They struggle to accurately model the fuzzy probabilistic world of quantum mechanics. This is a problem because on the smallest scales the universe is quantum, and the very beginning of the universe, the Big Bang, was a quantum event. Our classical simulations can't really model what happened in that first fraction of a second. They also can't perfectly simulate things like the inside of a black hole, where quantum effects and gravity are both extremely strong. Quantum computers are a different kind of machine. They use qubits. A qubit can be a 0, a 1, or both at the same time, a state called superposition. This, along with another quantum property called entanglement, allows quantum computers to perform certain calculations exponentially faster than any classical computer ever could. A computer with just a few hundred stable qubits could, in theory, perform more calculations simultaneously than there are atoms in the known universe. With a powerful, large-scale quantum computer, we could build a true quantum simulation of the universe. We could model the behavior of space-time at the Planck scale. We could simulate the conditions of the Big Bang and see if it produces a universe with the properties we observe, like the amount of dark energy. We could create a virtual black hole and watch it evaporate via Hawking radiation, testing a theory that is currently impossible to test. This technology could solve some of the deepest mysteries. Why is there more matter than antimatter? We could simulate the early universe's particle interactions to find the asymmetry. What is dark energy? We could test different theories for the energy of empty space in a simulation to see which one matches reality. A quantum computer wouldn't be a telescope looking out at the universe. It would be a laboratory for creating and experimenting with virtual universes. It would allow us to test our most fundamental theories in a way that is otherwise impossible. We could tweak the laws of physics in the simulation, change the strength of gravity or the charge of an electron, and see what kind of universe results. This would give us a profound insight into why our universe is the way it is. Number 14A, microscope to see the fabric of space-time itself. We have microscopes that can see atoms, we have particle accelerators that can probe the structure of protons and neutrons, but we have no way to see the smallest possible scale of the universe. This is the Planck length, about 1.6 x 10 to the power of 35 meters. It's a scale so small that if an atom were the size of the known universe, the Planck length would be the size of a tree. At this scale, our current theories of physics, general relativity, and quantum mechanics break down. We believe that space-time itself is not smooth, but a chaotic, bubbling foam of quantum fluctuations. How could we ever see this? We can't build a traditional microscope to do it. The energy required to probe such small scales would be so immense that it would create a black hole. It's a fundamental limit, but there might be an indirect way. A concept, sometimes called a space-time microscope or a holometer, aims to do just that. The idea was tested in an experiment at Fermilab led by Craig Hogan. The principle is that if space-time is quantized and jittery at the Planck scale, this quantum foam might create a very subtle, random noise that affects the position of everything in the universe. The experiment used a pair of powerful parallel laser interferometers. These are like the detectors used to find gravitational waves, but designed to look for a different kind of signal. They measure their own relative positions with extreme precision. If space-time is fundamentally jittery, then the positions of the mirrors and the interferometers should be constantly randomly fluctuating by a tiny amount. This would show up as a specific kind of noise in the laser light. The Fermilab holometer ran from 2014 to 2016 and didn't find this holographic noise, ruling out some specific models of quantum space-time. But the idea remains powerful. Future, more sensitive versions of such an experiment could be built. perhaps in space, free from the seismic noise of Earth. If such a device ever detected this fundamental jitter, it would be a monumental discovery. You know, it would be the first direct experimental evidence of the quantum nature of gravity. It would prove that the smooth, continuous space-time of Einstein's theories is just an approximation. It would tell us what the universe is made of at its most fundamental level. Is it made of tiny loops, as in loop quantum gravity, or tiny vibrating strings? A space-time microscope wouldn't give us a picture, but it would let us hear the hum of the quantum foam, the basic graininess of reality. This would be the key to unlocking a theory of everything, a single framework that describes all forces of nature. Now, number 13, an artificial mind to find the patterns we can't see. Modern astronomy is a data problem. The Vera C. Rubin Observatory, set to begin its survey in 2025, will generate about 20 terabytes of data every single night. That's more data each night than the Hubble Space Telescope has produced in its entire 30-plus years of operation. Over its 10-year survey, it will map the entire southern sky hundreds of times, cataloging billions of stars and galaxies. No team of human astronomers could ever hope to sift through all that information. This is where AI comes in. But we're not just talking about simple pattern recognition algorithms. We're talking about a future technology, an autonomous AI cosmologist. This would be an AI system specifically designed to do science. You know, it would not just be a tool for humans, it would be a research partner. You would give it access to all our astronomical data from Rubin, from the James Webb Space Telescope, from gravitational wave detectors, from every source we have. You would also give it all our current theories of physics. Its job would be to find the discrepancies. The AI would search for correlations and anomalies that human brains, with our inherent biases and limited processing power, would never notice. For example, it could analyze the precise motions of a billion stars in a distant galaxy and notice a subtle wobble that doesn't fit our models of dark matter. This could point to a new property of dark matter, or even a new force of nature. It could scan millions of supernova explosions and find a small subset that dim in a way that contradicts our standard model of cosmology, hinting at a flaw in our understanding of dark energy. A truly advanced AI cosmologist could even formulate its own hypotheses. It could generate new mathematical models and then devise observational tests for those models. It might say, based on this anomaly in the cosmic microwave background, I hypothesize a new type of particle existed in the early universe. To test this, you should point a radio telescope at this specific patch of sky and look for this exact signal. It would essentially be accelerating the scientific method. This technology is already starting to emerge. AI has been used to discover new exoplanets in Kepler data and to find gravitational lenses. But a true AI cosmologist would be a qualitative leap forward. It would be able to connect the dots between different areas of physics, particle physics, cosmology, astrophysics, in ways we can't. The greatest discoveries of the 21st century might not be made by a human staring at a screen. They might be made by an AI that alerts us to a pattern in the noise, a signal from the cosmos that was hidden in plain sight, buried in a mountain of data too vast for us to climb. Number 12, using a planet as a ghost particle detector. The neutrinos are everywhere. Trillions of them are passing through your body every second. They are produced in the sun, in distant supernovas, and in the Big Bang itself. They are often called ghost particles because they barely interact with other matter. A neutrino could pass through a light year of solid lead with a 50% chance of not hitting a single atom. This makes them incredibly hard to detect, but it also means they carry information from places we can never see directly. They travel in straight lines from their source, undeflected by magnetic fields. Our Current neutrino detectors are huge. Super Kamiokande in Japan is a tank holding 50,000 tons of ultra-pure water buried deep underground. Ice Cube at the South Pole uses a cubic kilometer of Antarctic ice as its detector. They work by looking for the rare, faint flash of light that occurs when a neutrino happens to collide with an atom in the water or ice. Even with these massive detectors, we only catch a tiny fraction of the neutrinos passing through. A future technology would be a planetary scale detector. Instead of building a bigger tank, we would use a whole planet, or a large part of it, as the detector. One concept is called the Acoustic Thermino Interaction Experiment Atrium. The idea is to place a grid of highly sensitive hydrophones or underwater microphones deep in an ocean or a large sea. When a very high-energy neutrino collides with an atom in the water, it deposits a tiny amount of energy, creating a small, expanding bubble of heat. This creates a very faint, characteristic pop, or acoustic signal. By triangulating this sound with multiple hydrophones, scientists could pinpoint the interaction and determine the neutrino's energy and direction. An even more ambitious idea is to use the entire Earth's core or mantle. By placing seismometers around the globe, we could listen for the faint seismic vibrations produced by ultra-high energy neutrino interactions deep within the planet. This would turn our planet into a giant scientific instrument. Why go to such lengths? Because these high-energy neutrinos are messengers from the most violent events in the universe. They could come from the hearts of active galactic nuclei where supermassive black holes are devouring stars. They could be produced by gamma-ray bursts, the most powerful explosions known. They could also be created by the annihilation of dark matter particles. By detecting these neutrinos and tracing them back to their source, we could open a new window on the high-energy universe, where we could study the physics of black hole accretion, disks, and cosmic ray acceleration directly. It's the ultimate form of astronomy, using the most elusive particles to see into the most hidden and violent corners of the cosmos. Number 11A giant liquid eye on the moon to see the first stars. The James Webb Space Telescope has a primary mirror that is 6.5 meters across. The next generation of ground-based telescopes, like the Extremely Large Telescope, will have mirrors over 39 meters across. But there is a physical limit to how large you can build a solid mirror and launch it into space, or support it on Earth. There's a clever alternative, a liquid mirror. The concept is simple. You take a container of a reflective liquid like mercury and spin it at a constant speed. The surface of the liquid will naturally form a perfect parabola due to centrifugal force and gravity. A parabola is the ideal shape for a telescope mirror to focus light. Liquid mirror telescopes have been built on Earth. The Large Zenith Telescope in British Columbia had a 6-meter spinning mercury mirror. But on Earth, they have a major limitation. They can only look straight up at the zenith. They can't be tilted. But what if you built one on the moon? A lunar crater, especially one near the poles that is permanently in shadow, would be the perfect location. The moon has no atmosphere to distort the view. It has low gravity, which makes it easier to support the structure. And it rotates very slowly. A large, shallow crater could be lined with a reflective liquid. Because it's a liquid, the mirror could be enormous. A concept called the Ultimately Large Telescope proposes a 100-meter liquid mirror telescope in a lunar crater. This telescope would be incredibly powerful. A 100-meter mirror would have over 200 times the light collecting area of the James Webb Space Telescope. It would be able to see the very first stars that formed in the universe, the so-called population, the third stars. These stars, born from only the hydrogen and helium of the Big Bang, are thought to have been hundreds of times more massive than our sun and to have lived very short, violent lives. We have never seen one directly. A lunar liquid mirror telescope could capture their faint ancient light. It could also study the atmospheres of Earth, like exoplanets, in unprecedented detail. It could search for biosignatures like oxygen and methane in the air of planets orbiting other stars. The engineering challenges are significant. We would need to transport the materials to the moon and build the telescope using robotics. We would need to find a liquid that stays liquid at the frigid temperatures of a permanently shadowed crater, and that can be coated with a reflective layer. But the scientific payoff would be revolutionary. It would be the most powerful eye on the universe we have ever built, staring out from the silent, stable platform of the moon. Number 10. Building a machine to directly poke dark matter. Well, about 27% of the universe is made of dark matter. We know it's there because we see its gravity. It's the invisible scaffolding that holds galaxies together. Stars on the outer edges of galaxies are moving too fast. They should fly off into space. The gravity of the visible matter isn't enough to hold them. There has to be something else there, a huge halo of invisible matter. We see its effects in the way light from distant galaxies is bent by gravity, an effect called gravitational lensing. But we have no idea what it is. The leading theory is that it's made of a new type of subatomic particle, one that doesn't interact with light or with normal matter except through gravity. We've built incredibly sensitive experiments to try and detect these particles. Most are giant vats of a special liquid like xenon buried deep underground to shield them from cosmic rays. The idea is that very rarely a dark matter particle might bump into one of the xenon nuclei, creating a tiny flash of light that our sensors can pick up. So far, experiments like LUX and Xenon 1T have found nothing. This suggests we might need a new approach. Instead of waiting passively for a dark matter particle to hit our detector, what if we could build a machine that actively creates a field that interacts with dark matter? This is, of course, highly speculative, as we don't know what dark matter is, but let's assume it interacts via some unknown, very weak force in addition to gravity. A direct dark matter interaction field would be a device that generates an energetic field tuned to this hypothetical force. Imagine a large shielded room. In the center is a device that broadcasts this new field. The field itself wouldn't affect normal matter, but if a dark matter particle passed through, it would be affected. It might be deflected, it might be excited, and then release a detectable particle when it decays. We could surround the room with detectors and look for these signals. It's like trying to find an invisible ship in the ocean. You know, instead of just listening for its engine, you send out sonar pings and listen for an echo. This device would be our dark matter sonar. The challenge is that we don't know what frequency to ping. We don't know what this new force looks like. Building such a device would require a breakthrough in theoretical physics first. We'd need a better candidate theory for what dark matter is and how it might interact. But if we could build it, we could finally prove that dark matter particles are real. We could measure their properties, their mass, their spin, how they interact. We could start to map the dark matter halo of our own galaxy directly, not just by its gravitational effects. It would be like turning on a light in a dark room that we previously only knew existed because we kept bumping into the furniture. Number 9. Using the sun as a giant telescope lens. In 1919, an observation of a solar eclipse proved that massive objects bend light, just as Einstein's theory of general relativity predicted. The sun's gravity acts like a lens. This is called gravitational lensing. We use it all the time in astronomy to study distant galaxies that are magnified by the gravity of a closer galaxy cluster. But there is a very special and much more powerful version of this effect. If you go far enough away from the sun, to a distance of about 550 astronomical units AU, or 550 times the distance from the Earth to the Sun, something amazing happens. At this distance, the sun's gravity focuses the light from a distant object not to a single point, but to a line that extends outwards. This is called the Solar Gravitational Lens, SGL. The Voyager 1 probe is currently at about 160 AU to give a sense of the immense distance involved. The magnification power of the SGL is staggering. A 2017 study by scientists at NASA's Jet Propulsion Laboratory calculated that the SGL could achieve a magnification of up to 100 billion. With this level of magnification, a 1-meter telescope placed on the focal line could, in theory, directly image an exoplanet orbiting a star 100 light-years away with a surface resolution of about 10 kilometers per pixel. This means we wouldn't just see a dot. We could see continents, oceans, clouds, and maybe even city lights, if they existed. We could map the surface of an alien world. To use the SGL, we would need to send a fleet of small spacecraft to this distance of 550 AU and beyond. Each spacecraft would be a small telescope. To image an exoplanet, they would have to be positioned with incredible precision on the focal line, directly behind the sun, from the target star's perspective. The sun itself is a problem. Its corona, the hot gas surrounding it, would distort the image. So the spacecraft would need to analyze the light and use sophisticated image processing to correct for this noise. Getting there is the biggest hurdle. With current propulsion, it would take over a century. We would need advanced propulsion like solar sails or fusion rockets to make the journey in a more reasonable 20 to 30 years. But the potential is unmatched by any other telescope concept. The SGL would turn science fiction into reality. We could answer the question, are we alone, not by looking for ambiguous radio signals, but by taking a direct photograph of a living, breathing world. We could study its climate, its seasons, and its geology from afar. It's the ultimate telescope, a gift from the laws of physics, using our own star to see the universe in a way we never thought possible. Number 8, the search for a hidden force of nature. We know of 4 fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. These 4 forces, described by the standard model of particle physics and general relativity, explain almost every physical phenomenon we have ever observed. But there are hints that this is not the whole story. The anomalous magnetic moment of a particle called the muon, measured at Fermilab, doesn't quite match the predictions of the standard model. The accelerating expansion of the universe driven by dark energy is a complete mystery. Dark matter itself might interact with our world through a force we don't know about. These anomalies could be pointing to the existence of a 5th force. This wouldn't be a force like we see in movies. It would likely be very weak, or only act over very short or very long distances, which is why we haven't found it yet. A 5th force detector would be a new kind of experiment designed specifically to look for these subtle deviations from our known laws. There are many ways to build one. Some experiments look for tiny variations in the strength of gravity over very short distances, millimeters or less. If there is a new force carrier particle that only travels a short distance, it would show up as a change in the inverse square law of gravity at that scale. Other experiments look for evidence of new extremely light particles like the proposed action, which could be a component of dark matter. The AtomX experiment, for example, uses a powerful magnetic field and a resonant microwave cavity to try and convert actions into detectable photons. A future 5th force detector could be a massive space-based experiment. Imagine 2 satellites in a very precise orbit, their distance measured constantly by lasers. If they passed through a region with a gradient in a new unknown field, their orbits would be perturbed in a way that gravity alone cannot explain. We could also look for violations of the equivalence principle, the idea that gravity accelerates all objects equally regardless of their composition. An experiment could drop 2 objects made of different materials in a vacuum and measure their acceleration with unprecedented precision. If there is a 5th force that couples to, say, the number of neutrons in an atom differently than the number of protons, one object would fall slightly faster than the other. Finding a 5th force would be a revolution in physics. It would be the first major crack in the standard model. It would tell us that our inventory of the universe's basic ingredients is incomplete. It could provide a portal to the dark sector, explaining how dark matter might interact with itself or with us. And it would open up a whole new realm of physics to explore. It would be like discovering a new color, a new sound, a new fundamental aspect of reality that has been hiding from us all this time. Number 7, a clock so precise it can measure the warping of space-time. The best atomic clocks today are incredibly precise. A strontium lattice clock, for example, is so accurate that it would not lose or gain a second in 15 billion years, which is longer than the current age of the universe. These clocks work by using a laser to measure the very regular, predictable vibrations of atoms. But we can do even better. A nuclear clock is a future technology that would be based on the vibrations of an atomic nucleus rather than the electrons orbiting it. The nucleus is much smaller and much better shielded from external noise like magnetic and electric fields. This would make a nuclear clock even more stable and precise. The leading candidate for a nuclear clock is an isotope called thorium-229, which has an excited state with an unusually low energy, making it accessible to lasers. Building a working nuclear clock is a major challenge in experimental physics, but labs around the world are getting closer. What could you do with a clock that is 10 or 100 times more precise than our current best? You could test fundamental physics in new ways. Einstein's theory of general relativity predicts that time runs slower in a stronger gravitational field. This is called gravitational time dilation. We have measured this effect. A clock at sea level runs slightly slower than a clock on a mountain. With a network of hyper-accurate nuclear clocks, we could measure this effect with incredible precision. We could use it for a new kind of geodesy, mapping the Earth's gravitational field by measuring tiny differences in the passage of time. More profoundly, we could use it to search for new physics. Some theories that try to unite gravity and quantum mechanics predict that the fundamental constants of nature, like the fine structure constant that governs the strength of electromagnetism, might not be truly constant. They might change very slightly over time, or they might be different in a strong gravitational field. By comparing a nuclear clock, which is sensitive to the strong nuclear force, with an atomic clock sensitive to electromagnetism over many years, we could detect such a change. This would be evidence for new physics beyond the standard model. We could even use these clocks to detect gravitational waves in a new frequency range, or to search for certain kinds of dark matter. Some dark matter models predict that it exists as a large oscillating field. As this field washes over the Earth, it would cause the fundamental constants to oscillate very slightly, which would show up as a tiny, regular wiggle in the ticking of our best clocks. A network of synchronized nuclear clocks would become a new kind of observatory, a cosmic sensor that doesn't look at light, but at the very fabric of time itself, listening for the faint ticks and wobbles that could signal the presence of unknown physics. Number 6, listening for the cracks in the early universe. The Big Bang was not perfectly smooth. Quantum fluctuations in the very first moments of the universe were stretched to astronomical sizes by cosmic inflation. These fluctuations became the seeds for the galaxies and clusters of galaxies we see today. But some theories predict that the rapid cooling and phase transitions of the early universe could have also created large-scale defects in the fabric of space-time itself. These are called cosmic strings. A cosmic string would be a one-dimensional object, a line of pure energy, thinner than an atom but potentially stretching across vast regions of space. They would be incredibly dense, with a small segment a few meters long having the mass of the Earth. They are not the same as the strings in string theory. They are a prediction of some grand unified theories that try to unite the fundamental forces. If they exist, they would be a fossil from the first second of the universe's existence. How would we find them? A cosmic string passing through space would dramatically warp space-time around it. If a string passed between us and a distant galaxy, it would act like a strange lens, creating a double image of the galaxy. We could search for these specific lensing signatures. More excitingly, a moving, vibrating cosmic string would radiate gravitational waves, not the short bursts from merging black holes that LIGO detects, but a continuous stochastic background of waves. Future, more sensitive gravitational wave detectors, especially space-based ones like LISA, could be able to detect this faint, persistent hum of gravitational waves from a network of cosmic strings stretching across the cosmos. Another possibility is that a cosmic string loop could collapse. This would release a huge burst of high-energy particles and radiation, which we might detect as a fast radio burst or a gamma-ray burst with no obvious source, like a supernova. Finding a cosmic string would be a direct confirmation of our theories about the physics of the very early universe. It would tell us about the energy scale at which the fundamental forces unified. It would be like finding a preserved artifact from the archaeological dig of the Big Bang. A cosmic string observatory would not be a single telescope, but a coordinated effort using gravitational wave detectors, radio telescopes, and optical surveys, all looking for the specific weird signatures that these exotic objects would leave on the universe. They are a long shot, but if we found one, the payoff in terms of our understanding of cosmic origins would be immense. Number 5. Hearing the symphony of the universe in gravitational waves. In 2015, the LIGO experiment detected gravitational waves for the first time. It was the chirp of two black holes spiraling into each other and merging. This opened a new way to study the universe. Instead of looking at light, we can now listen to the vibrations of space-time itself. LIGO and its partner Observatory Virgo are sensitive to high-frequency gravitational waves, the kind produced by the merger of stellar mass black holes and neutron stars. But this is like listening to a symphony and only being able to hear the piccolo. There is a whole spectrum of lower frequency gravitational waves that we are currently deaf to. These waves are produced by much larger events, the merger of supermassive black holes, millions or billions of times the mass of the sun, which sit at the center of galaxies, would produce very low frequency waves. The inspiral of a smaller black hole into a supermassive one would also create a distinct signal, and the very early universe during the period of cosmic inflation may have produced a primordial background of gravitational waves that still fills the universe today. To hear these low-frequency sounds, we need a much bigger detector. We need to go to space. The Laser Interferometer Space Antenna LISA is a mission planned by the European Space Agency for the 2030s. It will consist of 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers. They will be connected by lasers. A passing gravitational wave will stretch and squeeze the distance between the spacecraft by a tiny amount, less than the width of an atom. LISA will be able to detect this change. LISA will open up a new gravitational wave window on the cosmos. It will be able to detect the merger of supermassive black holes anywhere in the universe, all the way back to the time of the first galaxies. This will tell us how galaxies and their central black holes grow and evolve together. It will map the population of black holes in our own galaxy. It could detect thousands of binary star systems. Most importantly, LISA might be able to detect the gravitational wave background from the Big Bang. This would be a signal from the first 10 to the power of 32 seconds of the universe's existence. Light can only show us the universe as it was 380,000 years after the Big Bang, when the cosmic microwave background was released. Gravitational waves come to us directly from the event itself. Detecting this primordial background would be a direct confirmation of cosmic inflation. It would be like hearing the sound of the Big Bang. Future, even more ambitious space-based detectors with even longer arms could probe even lower frequencies, searching for new physics and unknown cosmic events. This technology will transform cosmology from a silent movie into a full sensory experience. Number 4. Building a trap for the universe's missing matter. In the Big Bang, matter and antimatter should have been created in equal amounts. Matter and antimatter are mirror images of each other. A proton has a positive charge, an antiproton has a negative charge. An electron is negative, a positron is positive. When a particle and its antiparticle meet, they annihilate each other in a flash of energy. This leads to a huge problem. If they were created in equal amounts, they should have all annihilated each other in the early universe, leaving nothing behind but a sea of radiation. But we are here. The planets, the stars, the galaxies, they are all made of matter. For some reason, there was a tiny imbalance. For every billion antimatter particles, there was about 1,000,001,000 matter particles. All the antimatter annihilated with most of the matter, and the small leftover amount of matter formed the entire universe we see today. We have no idea why this asymmetry exists. It is one of the biggest unsolved mysteries in physics. To study this, we need to study antimatter itself. We can create it in small amounts in particle accelerators like at CERN. In experiments, there have managed to create and trap antihydrogen atoms and antiproton orbited by a positron for short periods. The goal is to study them with extreme precision. Does antimatter behave exactly like matter? Does it fall down in a gravitational field, or does it fall up? Most physicists are almost certain it falls down, but it hasn't been definitively proven experimentally. Are its energy levels exactly the same as hydrogen's? A tiny difference could be a clue to solving the matter-antimatter asymmetry problem. A future antimatter factory would be a dedicated facility for producing and storing large amounts of antimatter. This would allow for more precise and varied experiments. We could create anti-helium or even heavier anti-atoms. We could build an antimatter telescope. An antimatter telescope wouldn't look for light. It would look for the specific gamma rays produced when an antimatter particle, like an antiproton, hits normal matter in space and annihilates. This could tell us if there are any regions of the universe, like entire galaxies, that are made of antimatter. The current consensus is that there are not, because we don't see the massive gamma ray glow from the boundaries where they would meet matter galaxies. But we need to be sure. The technology for trapping antimatter is based on strong magnetic and electric fields, holding the charged antiparticles in a vacuum so they don't touch the walls of the container. Storing significant quantities is a monumental engineering challenge, but being able to produce and study antimatter in detail is crucial. The answer to why we exist at all might be hidden in a subtle difference between a particle and its mirror image. Number 3, a better picture of the universe's baby photo. The cosmic microwave background CMB is the oldest light in the universe. It's the afterglow of the Big Bang, released about 380,000 years after the event, when the universe cooled enough for neutral atoms to form. Before that, the universe was an opaque, hot plasma. The CMB is a snapshot of the infant universe. Telescopes like COBE, WMAP, and Planck have created incredibly detailed maps of the CMB. These maps show tiny temperature fluctuations, differences of just a few parts in 100,000. These tiny ripples were the seeds that grew into all the cosmic structures we see today. The CMB has been a treasure trove for cosmology. By studying the statistical properties of these spots, we have determined the age of the universe, its composition, how much normal matter, dark matter, and dark energy it contains, and its geometry. But there is more information locked away in this ancient light. The light of the CMB is also polarized, like the light that reflects off a road and can be blocked by polarized sunglasses. This polarization comes in two patterns called E modes and B modes. The E modes have been detected, and they are caused by the scattering of light-off electrons in the early universe. The B modes are the real prize. There are two potential sources for them. One is gravitational lensing, where the gravity of massive structures distorts the CMB light as it travels across the universe. This has been detected. The other, much fainter source is primordial gravitational waves produced during cosmic inflation in the first fraction of a second of the universe's existence. Detecting these primordial B modes is the holy grail of modern cosmology. It would be irrefutable proof of inflation and would give us a direct look at the physics of the universe at unimaginable energies. A future high-resolution CMB telescope would be a dedicated observatory, either on the ground in a very dry place like the Atacama Desert or the South Pole, or in space. It would have many more and much more sensitive detectors than our current experiments. It would be able to map the polarization of the CMB with exquisite precision. The Simons Observatory and CMB S4 are next-generation ground-based projects designed to do just this. A future space mission, going beyond Planck, could make an even cleaner measurement free from atmospheric interference. By separating the faint B-mode signal from the foreground noise of our own galaxy's dust, these future telescopes could give us our first direct evidence of what happened in the moment of creation. It would be like finding a hidden message in the universe's baby picture, a message that tells us about the very instant it was born. Number 2, a machine bigger than a city to recreate the Big Bang. The Large Hadron Collider, LHC, at CERN is the most powerful particle accelerator ever built. It's a 27-kilometer ring of superconducting magnets that smashes protons together at close to the speed of light. These collisions recreate the energy conditions of the universe a fraction of a second after the Big Bang. By studying the debris of these collisions, physicists discovered the Higgs boson in 2012, the particle that gives other particles mass. The LHC has been a huge success, but it has also left us with many questions. It hasn't found any evidence for supersymmetry or other theories that were proposed to solve problems like the nature of dark matter. To push further, to probe even earlier moments in the universe's history and higher energy scales, we need a bigger, more powerful machine. Several concepts for a next-generation particle accelerator are being discussed. One is the Future Circular Collider FCC, a proposed 100-kilometer ring to be built at CERN. It would be nearly 4 times the size of the LHC and could collide particles with 7 times the energy. It would be a Higgs factory producing millions of Higgs bosons to study their properties with incredible precision. Any deviation from the predictions of the standard model could point to new physics. Another idea is a linear collider, like the proposed International Linear Collider ILC. Instead of sending particles in a circle, it would accelerate them in 2 long straight lines and smash them together in the middle. A linear collider would provide cleaner collisions that are easier to analyze. These machines are massive undertakings, costing tens of billions of dollars and taking decades to build. But they are our only way to directly test the laws of physics at the highest energies. And a future accelerator could discover the particles that make up dark matter. It could find evidence for extra dimensions of space. It could help us understand why gravity is so much weaker than the other forces. Particle accelerators are a type of microscope, but instead of using light to see small things, they use energy. The higher the energy of the collision, the smaller the scale you can probe. The LHC is probing the physics of a trillionth of a second after the Big Bang. A machine like the FCC would push that back even further. It is our only way to travel back in time, to recreate the primordial soup of the early universe in a controlled laboratory setting here on Earth. The mysteries of the cosmos, like dark matter and dark energy, are fundamentally problems of particle physics. A bigger accelerator is our best tool for finding the answers. Number 1, a giant space umbrella to take a picture of another Earth. We have discovered thousands of exoplanets, planets orbiting other stars. We've found them mostly by indirect methods, like watching a star's light dim slightly as a planet passes in front of it, the transit method, or looking for the slight wobble in a star's position caused by the gravitational tug of a planet, the radial velocity method. These methods tell us a planet exists, how big it is, and how far it is from its star. But they don't give us a picture. Directly imaging an Earth like exoplanet is incredibly difficult. The problem is that the star it orbits is about 1 billion times brighter than the planet. The faint light from the planet is completely washed out by the glare of its star. It's like trying to see a firefly sitting next to a searchlight from miles away. There are two main future technologies designed to solve this problem. The first is an advanced coronagraph. A coronagraph is a device inside a telescope that blocks out the light from the star, allowing the much fainter light of the planet to be seen. The Nancy Grace Roman Space Telescope, launching in the mid-2020s, will have a technology demonstrator coronagraph that will be thousands of times more powerful than previous ones. The second, and even more ambitious, technology is a starshade. A starshade is a separate spacecraft, a large, precisely shaped screen, perhaps 30 to 50 meters across, shaped like a sunflower. It would fly tens of thousands of kilometers in front of a space telescope in a very precise formation. The starshade would be positioned to block the light from a target star, casting a very dark shadow over the telescope. From within this shadow, the telescope could then observe the faint light from the planets orbiting that star without being blinded by the starlight. This combination of a large space telescope and a starshade would be a true Earth finder. It could take an actual picture of an Earth-sized planet in the habitable zone of a nearby star. It wouldn't be a detailed picture like a photo of Earth from the moon. It would just be a dot of light. But we could analyze that dot by passing the planet's light through a spectrometer. We could see what its atmosphere is made of. We could look for the telltale signs of life oxygen, methane, water vapor. We could see if it has clouds. By observing it over time, we could determine the length of its day and see if it has seasons. This is perhaps the most profound search in all of science. It seeks to answer a question that humans have asked for millennia. Are we alone? A direct exoplanet imager, whether using a coronagraph or a starshade, is the technology that could finally give us the answer. It could show us a pale blue dot orbiting another sun, a world that might harbor life. This is not a technology for probing the beginning of time or the nature of reality. It's for finding our neighbors.